I want to talk about charging a capacitor. So far we've talked about electrostatics, when charges don't move. And then we talked about when charges do move, called currents. But so far we've only talked about currents that have existed for a long time. Steady currents, not changing currents. So we're going to talk a little bit right now about changing currents, and specifically how we might charge up a capacitor and how the current through a circuit might vary as I charge a capacitor up. So here I've got a basic circuit drawn here, and we would call this an RC circuit. Why do we call it an RC circuit? Well, we have a light bulb, and remember, a light bulb is simply a resistor that does something useful, gives off light. And here we have a capacitor. So this is an RC circuit. Now, we want to talk about an RC circuit that has a switch in it. Okay, so here we have a switch in my RC circuit. With the switch open and the capacitor discharged, nothing happens. That's not very exciting. You probably would have guessed that. My question is, what will happen when I first close the switch? So here I have this exact same setup. I have my battery. It is coming through here. This wire is connected to one side of my capacitor. I've got the other side of the capacitor hooked here, and it goes through my light bulb. And right now my switch is open because I have not connected up my light bulb. And it goes back here to the battery. So what I'm going to do now is I'm going to hook up my switch. And first, I want you to think to yourself, what will you observe in the light bulb? Will the light bulb be bright right away and then get dim? Dim then bright? Something else? I don't know. Make a prediction. I'll see you on the other side. Okay, hopefully you made a prediction. Let's see it. Here we go. Wow! I hope you were as impressed as I am. What did we observe? We observed that the light was bright at the beginning, and then it slowly decayed and became less and less bright. That's interesting. So that's pretty interesting, right? And remember that we can use the brightness of this light bulb as sort of a current meter, an ammeter almost, if you will, or as a proxy for current, where the brighter the light bulb is, the greater the current is. So hopefully we concluded that we saw a varying current in this circuit. It started with a large current and a bright light bulb, and then the current slowly decreased until now, here we are, there's no current at all. The light bulb is not glowing at all, yet the battery is still hooked up. Interesting. Now let's see what happens when we discharge the capacitor. Okay, so now I'm going to change my circuit. I'm going to change it so that the battery is completely removed. I'm going to have a charged up capacitor, and I'm going to close my switch and discharge the capacitor through the resistor. Let's set that up. Okay, so now my battery is gone. I have my light bulb and my capacitor, which is now charged up because I just charged it up. Well, I want you to predict what will happen when I close the switch by connecting this wire right here. Hopefully you predicted. Let's see. Whoa! Power! Current! Interesting. Very, very interesting. And the light bulb is out. So what did we observe here? Very similar behavior, didn't we? First we had a large current with a bright light bulb, and then over time it slowly decreased to nothing, which is the situation now. Let's check out some math. So here we see a schematic of the discharging of the capacitor. So this would be analogous to the second demonstration that I just did. So here we see a charged capacitor, and with the switch open, the charge just hangs out on the capacitor, nothing flows, not very interesting. Initially, we could calculate the voltage on the capacitor, which is just Q over C. Of course, this comes from our definition of capacitance. So immediately after the switch closes, we get a current here. We get a current. And notice that initially, the current is simply this initial voltage divided by the resistance. That's just Ohm's law. So the initial current is simply the initial voltage of the capacitor divided by the resistance in the circuit. And so that's our initial current. We get this nice bright bulb right when I flick the switch. But as that current flows, charge gets pulled off of the capacitor, and so the charge is lower on the capacitor. Therefore, the voltage across the capacitor is lower. Therefore, there's a smaller current. Therefore, our light bulb would not be as bright. All things we observe. At some point, that current actually goes to zero because the capacitor is completely discharged. And so we get these curves here where we see the current decaying off to zero right alongside the voltage on the capacitor decaying to zero. Now notice it's not linear. Right? These are exponential curves. And so we need to have an exponential equation for this, and indeed we do. So the decays of the voltage and the current are exponential decays. Here's this equation right here. I equals I naught, e to the negative t over RC. And the voltage across the capacitor is simply given by this equation here. Notice that these have an identical shape. We see that in the graphs. If we look at them, the only thing different here is the scale on the vertical axis. They have the exact same shape. And we see that in the equations as well. It's just some initial value times this e to the negative t over RC, some initial value times e to the negative t over RC. What's this initial value? Well, this is, remember what this symbol represents. It is the voltage applied across the capacitor. And the naught indicates initially, and then this indicates at some time. Be careful, a lot of times students see this delta, and we always think of delta as the change, and so we think of, this must be V final minus V initial. Ooh, it's not quite. We don't mean final minus initial in this case. In this context, right, the delta means what is the change in voltage from one side of the capacitor to another. So in other words, this is a delta V at one instant in time, not in two instants of time. So we have to be a little bit careful with that. Okay, so again, we observed this with our own eyeballs just a few moments ago. Here is the math to match what we just observed. Now, if we were to look back at this at these graphs right here, we could say, well, how long does it actually take for the current to go to zero? Well, an exponential curve never actually reaches zero. It gets asymptotically closer to zero, or closer and closer and closer and closer to zero as time goes on, but it never actually reaches zero. So we can't just solve this and say, oh, plug in zero for the current and solve for time, because it doesn't ever actually mathematically get there. It effectively goes to zero. We all saw the light bulb go out with our own eyes. So it effectively goes to zero at some point, but literally, technically, mathematically, it never goes to zero. So we introduced this idea of the time constant. And the time constant is like a characteristic time for the circuit. Since we can't really say how long does it take for the current to go to zero, instead we say, well, how long does it take for the current to fall to 37% of its original value? And that time constant, that's, if we multiply R times C, the resistance times the capacitance, surprisingly, we get units of seconds out. And so the resistance of the circuit times the capacitance of the circuit determines how quickly the circuit will discharge. A larger capacitor or a larger resistor means it takes longer for the circuit to discharge. And again, we can't say how long it takes to completely discharge, so we somewhat arbitrarily pick this number of 37% and say, well, let's use that value. Why 37%? Because this number E, it turns out to be just a real useful quantity in calculus and other applications. So we don't need to get into why 37%, but it's just convenient mathematically. We could have picked a different amount of time. We could have picked a half-life or something like that. We didn't, right? We picked, the time constant is how long it takes to get to some value. But the point is, a larger time constant means a slower discharge. A smaller time constant means a quicker discharge. And so with that in mind, we can just rewrite those equations, substituting tau for RC. Notice that this isn't anything new. This is not new physics. It's the exact same equations we see here, but with the time constant plugged in for RC. Here's just a graph kind of representing what I'm talking about here. So after one time constant, we're at 37% of the original value. After two time constants, we're at 37% of 37%, or about 13% of the initial value, and so on. After three time constants, we'd be 37% of 37% of 37%, which is some other number. Okay. But that's the idea. Again, it never actually goes to 0, so we just need some number to characterize how quickly that happens. Let's do a quick exercise here. The following circuits contain capacitors that are charged to 5 volts. All of the switches are closed at the same time. After 1 second has passed, which capacitor is charged to the highest voltage? So again, they're starting off charged, we're discharging them. After a certain amount of time, 1 second, which capacitor still has the largest voltage? Why don't you try and figure this out, and I'll see you on the other side. So hopefully you recognize that in order for it to remain with the highest voltage, we want it to discharge the slowest. And so we are looking for which of these circuits has the largest time constant, the largest value of tau, or the largest product of R times C. So let's just go through these. Tau equals R times C. So for A, we have 2 ohms times 1 farad. I know it's surprising, but it turns out that an ohm times a farad is a second. And so this ends up being 2 seconds. Using similar logic, we multiply the capacitance times the resistance for B, and we get .94 seconds. For C, we end up with 3 seconds. And for D, 1.41 seconds. So, which one has the largest time constant? C has the largest time constant. Therefore, it will discharge the most slowly. Therefore, after 1 second, it will remain with the largest charge of these 4 circuits. Now let's look at charging a capacitor. Here we see the circuit that I set up initially in this lecture, the demonstration I did at the very beginning. In a circuit that charges a capacitor, once the switch is closed, the potential difference of the battery drives a current. Now, it's really important to recognize here that initially the capacitor is uncharged, right? And so recall that, a lecture or two ago, we talked about how when will charge stop flowing into a capacitor? Well, charge will stop flowing into a capacitor when the potential across the capacitor is equal to the battery potential. And then essentially, you get the battery trying to push the current one way, the capacitor trying to push the current the other way. At some point, those are pushing equally hard, and there is no more current flowing. Let's look at this situation, right? Initially, the capacitor is uncharged, so there's no voltage across it. So how much resistance does it have? I should be careful with that term because capacitors don't actually have resistance. So is it trying to prevent the current from flowing? Is it fighting against the battery? No, it's not, because there's no potential across it at all. Another way to say it is that first positive charge that I put on this capacitor, it requires no work to do it. So when I initially flip this switch closed, it's almost like the capacitor isn't there at all. Another way to think about it is that an uncharged capacitor acts just like a wire. An uncharged capacitor acts just like a wire. It just lets current pass freely. And so again, this will continue to happen until the voltage across the capacitor is equal to the battery voltage. And then you've got the battery trying to push the current clockwise. You've got the capacitor trying to push the current counterclockwise. Once those are equal, then no more current flows. So looking at this then, we get a very similar shape for the current, and we observed that, didn't we? The light bulb was bright at the beginning, and then it went off to 0 eventually. Now, the voltage across the capacitor, it goes a different way if we're looking at charging the capacitor. It starts at 0, and it increases until it reaches the value of the battery, at which point the current stops flowing. So we do get a little bit of a different form for the voltage across the capacitor if I am charging versus discharging. But notice that the current equation looks identical, whether I'm charging or I am discharging. The current equation is identical. Now, notice again we could replace the R times C with a tau. And again, to point out this initial value of the current, notice that the initial value of the current is given by simply the EMF of the battery divided by the resistance of the resistor. Why? Again, because an uncharged capacitor acts like a wire. It's almost like it's not there. What happens after a long time? After a long time, the current goes to 0. Looking back at this, that's because after a long time, a charged up capacitor acts like an open switch. So an uncharged capacitor acts like a wire. A completely charged capacitor acts like an open switch and prevents the current from flowing. Let's do an example. So here we have a circuit. The switch is initially closed and the bulb glows brightly. So initially the switch is closed and we have a nice current going right like this, okay? When the switch is opened, what happens to the brightness of the bulb? Will it just not be affected? Will it start at the same brightness and then gradually dim? Will the bulb start at the same brightness and then gradually brighten? Will it be initially bright and then dim, or will it initially dim and then brighten again? Why don't you think about this, and I'll see you on the other side. So this is our initial situation. The switch is closed, so this is basically like a wire over here, and the bulb is glowing. Well, what path does the current take here? Well, the current, I, is going to travel like this. So that is the path that the current will take. Now, what is the voltage across the capacitor right now? It's 0. There is no charge on the capacitor. How can I tell? Because both ends of the capacitor are connected with a wire. An ideal wire has no resistance. So if both ends of my capacitor are connected, there's absolutely, definitely no charge on that capacitor. So this is the initial situation. Once I open the switch over here, well, now no current can flow over there. It's almost like this isn't there at all. It's almost like it's not there at all. Now what will the current do? Well, now it can't go over there. Now it has to go right here. We're going to charge that capacitor up. We've already seen this. For a charging capacitor, the current starts high and then dims to nothing. So the bulb, let's see, starts at the same brightness and then gradually dims. I believe describes that exactly, and indeed. So even though this is worded kind of goofily, this is really just asking you, what do we observe when we're charging a capacitor? How about this one? The capacitor is initially uncharged. Immediately after the switch closes, what is the capacitor voltage? Let's pause the video, and I'll see you on the other side. Okay, the capacitor is initially uncharged. Remember, Q equals C times V. If there's no charge, there's no voltage either. So right when I throw the switch, there's no charge on the capacitor, and the current just flows right through it. Let's do a numerical example. So here we've got this circuit here. The switch in the circuit has been in position A, so as shown here, for a long time, and the capacitor is fully charged. The switch is thrown to position B at t equals 0. What is the current in the circuit immediately after the switch is closed? Well, let's answer that first. So initially, we've got the initially we've got the switch in position A. And so this capacitor is fully charged. So after some long amount of time, there's 9 volts across this capacitor, isn't there? There's 9 volts across that capacitor. So when I go ahead and I throw this to position B, at that instant, there's still 9 volts across that capacitor. And so the current can be calculated quite easily. I equals the voltage across the capacitor initially divided by the resistance. And so we can just crank this through. And again, initially it's at 9 volts because it was fully charged, divided by 10 ohms. And we get 0.9 amps. Not too bad. Not too bad. Now, what is the current in the circuit 25 microseconds later? Well, think to yourself, should we get a smaller value, a bigger value, 0? We should get a smaller value, right? Because as this capacitor discharges, the current should go down. And so we're going to want to look up the equation for the current in a discharging capacitor. And it looks like this. So we really can just plug in here. We've got 0.9 amps, e to the 25 microseconds, divided by 10 ohms times 1 microfarad. Notice here that if an ohm times a farad is a second, then an ohm times a microfarad must be a microsecond. And so as long as we've got microseconds over microseconds, everything's good. We just can't have any units in that exponent. And so as long as we've got like units on both sides of that fraction, we're all good. And so we can just run our calculator at this point, and we get our number, which is 0.074 amps. All right, let's take a minute and see if that makes sense. Is it less than 0.9? Yes, it is. How many time constants have passed? Well, the time constant for this circuit is 10 ohms times 1 microfarad. So the time constant for this circuit is 10 microseconds. So we've about 2.5 time constants has passed in this circuit. And so we should expect something, you know, fairly small, and indeed this is. This is less than 10% of the original current. So I think this makes sense. It all jives.